Your role as a commissioning agent is defined as a legal auditor of the electrical grid. Your objective? To validate that every installation matches the approved engineering blueprints exactly as specified. This validation process operates under an absolute governance directive. We draw our testing parameters from international authorities like the IEC and IEE. If a project specification, manufacturer instruction, and standard conflict, you are required to enforce the most stringent approved requirement. These overarching standards cannot execute a test alone. Before you touch any equipment, you must extract site-specific variables from the project drawings. You confirm the accuracy tolerances for your specific meter class, identify designated OEM software versions for your laptop, and ensure every single instrument you use carries an active calibration certificate. Site preparation begins with a universal securance protocol. The isolation mandate is absolute. You apply strict lockout and tagout controls, isolate the test boundary with safety warning tape, apply proper personal protective equipment, and install temporary grounds. You must visually confirm the total absence of any unintended live electrical exposure. Unwavering compliance with this preliminary paperwork and physical isolation creates the legally recognized foundation for field safety before physical testing begins. Procedure 14.1 details the testing of advanced metering infrastructure. Testing AMI requires validating a continuous data pipeline from the physical meter out to the control center. Execution begins with a mandatory visual and mechanical inspection. You check terminal tightness and verify the meter health LEDs before any current is applied. Next, we establish the physical connection using controlled secondary injection. You route test leads from the Omicron unit into the red, yellow, blue, and neutral phases. With the injection active, the voltage, current, power, and frequency readouts must track the pushed values. Step 5 introduces energy accuracy testing. Here, you physically mount an optical photo head directly over the revenue meter's pulse port. During operation, the revenue meter emits light pulses. The photo head registers every individual watt and VARh energy pulse the meter generates. You record these pulses across selected current percentages and power factors. To determine accuracy, you calculate the percentage error by comparing these recorded optical pulses against your baseline injected values to verify it falls within the project's approved tolerance. By successfully capturing these optical pulses, you translate electrical power flow into auditable, verifiable digital data points. High-stakes revenue meters require a specific edge case verification, known as the creep test. This stress test ensures the meter does not record energy usage during extreme, unbalanced grid conditions. You execute this by injecting exactly 120% of the meter's rated voltage, while simultaneously holding the current at absolute 0 amps. To pass, the meter must prove it remains completely dormant. You verify that there is absolutely 0 pulse direction or rotation under this overvoltage state. Any pulse recorded during this state indicates a logic flaw. That specific failure results in false, artificially inflated billing for the consumer. Procedure 14.2 shifts focus to legacy analog and digital meters. Here, the primary objective changes. Instead of validating a network data link, you are validating a physical mechanical scale. The initial setup requires precise physical verification. Before you energize any test leads, you must verify mechanical 0. You confirm that the analog needle rests on the 0 mark without any voltage applied. Because analog gauges rely on physical springs, coils, and friction, taking a single data point does not provide sufficient evidence of accuracy. You must prove mechanical fidelity across the operational curve of the hardware. We accomplish this using the 3-point curve method. You step the injection values precisely through a low state at 25%, followed by the nominal and finally high states across the connected phases. At each step, you calculate the percentage error. You do this by comparing the physical needle indication against the known injected value under every load condition. Mechanical checks are strict. If an analog needle oscillates, it indicates a mechanical defect. You inspect the terminal tightness. If tight and it still oscillates, halt and fail the inspection. Proving mechanical fidelity across this 3-point curve allows the hardware to be verified for use under live grid conditions. The testing protocol extends beyond the physical meter face. You must also validate the network transmission reaching the substation automation system and the energy control center. The connection back to the local gateway must remain clear, showing exactly 0 unresolved alarms on the control center interface. If hardware fails or the AMI triggers alarms during testing, you follow a non-intervention mandate. You immediately stop the Omicron injection, verify your output is at absolute 0 amps, and flag the defect in the project log. You do not dismantle equipment or attempt unauthorized repairs. Resisting the urge to repair broken equipment in the field preserves the legal chain of custody and ensures the grid is protected from undocumented modifications. Every procedure terminates at the witness hold point. An official reviewer validates that raw injection values track the displayed values and that all communication tests show 0 unresolved alarms. The reviewer also verifies the as-left restoration protocol. This is the final requirement before any site is abandoned. Restoration requires specific steps. You must close test links, reset selector switches, and replace all protective covers and tamper-evident seals to their normal operating condition. To secure final approval, you assemble the evidence package. This includes your annotated test sheets, the raw data logs exported directly from the Omicron, and all calibration certificates to obtain the physical witness signature. Through the assembly of this meticulously documented evidence package, a piece of inert hardware is officially validated and becomes a trusted node on the electrical grid.